Hello, welcome. My name's Angel. We have Brian and Efron, and we're presenting you our exhaust turbine for hybrid engines as a way to gather energy for hybrid cars.
For our proposed design, our team is planning to use a helical blade shape or turbine that we can implement into the exhaust pipe of an automobile. In this manner, we'll be able to recover some of the energy that comes out of the exhaust and be able to put it back into the system for reuse. The current design that we're proposing is a helical shape with a configuration of 4 blades, each of the blades which are rotated in 90-degree angles at each end. We predicted, based on our initial predictions, we went with this design because we're trying to minimize as much of the airflow restriction in order to maintain the performance of the engine. And through further testing and simulation, we'll be able to determine which will provide the best performance for the systems we're creating.
As far as how it works, we'll be implementing the axial turbine in the direction of the airflow of the exhaust gas just prior to the bend in an exhaust pipe. This will allow us to have the excess rotation exit through the exhaust and connect through into a generator or alternator to generate the electricity. The optimizations we'll be working on will be focusing on the airfoil design and the configuration of the blades to determine if the angle of rotation is acceptable or if we need to change the number of blades. As far as fabrication, we'll be utilizing fused deposition modeling, 3D printing to produce the blades and potentially the supports. We'll be fabricating many different blade designs to validate our simulation results, confirm, and we'll be hoping for a resolution of 100 microns for the density of the blades.
As far as global market, there's cars pretty much all over the world, and as we see from 2000 currently the hybrid car market has increased steadily. So as far as engineers are concerned, it's important to see how the market's going or how to design for the future. And these are some hybrid cars and trucks. We have passenger cars and light duty cars, and that's the market we're going after. As far as global environmental impact, so thinking globally, acting locally, the U.S., the EPA last year signed into regulation as far as the fleet average of cars is going to be 54.5 miles per gallon from the year 2017 to 2025. That doesn't mean all cars, and like for example, Ford will be that standard. It'll be a fleet of cars, so specific cars. So you can have really high efficient cars and low efficient cars, but the average will be 54.5. And that approximately will save 4 billion barrels of oil a year and reduce the greenhouse gases by 2 billion metric tons a year.
One of the biggest challenges for us when creating this energy recovery system is to maintain the positive efficiency of the overall design that we're trying to pull out. In order for us to achieve that, we have to limit the amount of back pressure that this attaching the turbine into the exhaust will create. That's why through our simulations and choosing the optimal blade, we'll be able to do this. Another challenge is the size limitations since it's an exhaust of 3 or 2 inches diameter, then we will have to be working with microsystems as micro bearings and be able to make sure that it all attaches properly. The motivation behind our project is, as mentioned before, we're trying to increase the overall efficiency. And if we're able to do this, we'll be able to provide a reduction in the fuel consumption, which will provide us with a lot of the industry reduction in the cost of using fuel for our transportation.
This is our tentative timeline through April of 2014. We'll be hoping to begin testing as well as during the ending phases of manufacturing in order to get initial results and alter the testing if needed, the manufacturing sort.
And as far as for cost analysis, this cost analysis is based on making an actual working prototype. That way we can validate our results that we can simulate through SolidWorks as far as the rotation of the blade and the efficiency of it. Our estimated cost came out to $1,215. And since it's real world applications, we did an hours for the whole term of the project and came out to 420 hours at $35, $14,700. So we were paid, I guess, too. to make this, that's a real world challenge. Thank you. Do we have any questions?
Yeah. I do have expectations that you'll do a cost-benefit analysis, show us that prediction, do analysis to demonstrate that you've got a predicted efficiency on this, and then demonstrate that this thing does actually make sense. Actually.
Yeah, like our biggest challenge is to see how many watts can we get out of the revolutions that since the pipe's gonna have the airflow, the revolution is gonna create enough power to be worth, incorporating into the hybrid engines to charge their huge battery packs, because they use 300-volt batteries, for example, like Prius. That's one of our challenges. But
We also have intentions to expand on other uses, such as the exhaust of a dryer in a household, or above the air conditioner, compressor, or in a rain gutter, things like that. Things that have higher flow or more density, which will increase the rotation speed.
Questions? Do you have any other questions?
it's pretty clear.
Yes.
You had when you talk about the cost, $85 an hour.
Yeah,
Where you got to $85 from?
that's what we're hoping to get.
You're hoping to get.
But that was like a real world analysis, basically, because 410 hours is from the beginning of the semester all the way through. Comes out to like spending 11, 12 hours each week individually on working on this report.
Yeah, with going with the budget of $14,000, just putting that as what it would cost for engineers to prototype this, but we'll be providing that means as our own cost of the time of work.
Might be more. I thought it was low.
It's all right.
Questions? No. That's great. Okay, now listen. Thank you very much.